Download this code from codegive.com, link in the description below. OK, let's break down the icpc NAC 2022 problem C, cram, provide a thorough explanation of the solution strategy, and offer a C++ code example. Problem statement, cram. You are given a rectangular grid of size n×m. You want to place dominoes, 1x2 or 2x1 rectangles, on the grid such that each domino must cover exactly 2 adjacent cells. 2. No 2 dominoes can overlap. 3. You want to place as many dominoes as possible. However, there's a twist. Some cells in the grid are blocked and cannot be covered by dominoes. Your task is to determine the maximum number of dominoes that can be placed on the grid. Input asterisk. Asterisk. The first line contains two integers, n and m, representing the dimensions of the grid, 1 less than or equal to n, m less than or equal to 100. Asterisk. The next n lines each contain m characters, where dot represents an empty cell and x represents a blocked cell. Output asterisk. Asterisk. Print a single integer, the maximum number of dominoes that can be placed. Example input asterisk. Example output asterisk. Understanding the problem. This is a classic problem that can be modeled as a maximum matching problem in a bipartite graph. Here's the connection. 1. Grid as a graph asterisk. Imagine the grid as a graph where each empty cell, dot, is a node. 2. Bipartite graph asterisk. Divide the empty cells into two sets based on the sum of their row and column indices, i.e., row plus col. Call them set A and set B. Cells in set A will have an even sum of row and column, and cells in set B will have an odd sum. 3. Edges asterisk. Create an edge between two nodes, cells, if they are adjacent, up, down, left, right, and are both empty cells. Crucially, one endpoint of the edge will belong to set A, and the other to set B. This is because adjacent cells will always have different sums of row and column indices. 4. Dominoes as matching asterisk. Placing a domino on two adjacent empty cells is equivalent to finding a matching edge in the graph. A matching is a set of edges where no two edges share a common node. 5. Maximum matching asterisk. The maximum number of dominoes you can place is equal to the size of the maximum matching in this bipartite graph. Solution strategy, using max flow. While there are algorithms specifically for finding maximum matchings, example Hopcroft-Karp, we can also use a standard max flow algorithm to solve this problem. Here's how to transform the bipartite matching problem into a max flow problem. 1. Add a source and a sink asterisk. Asterisk. Create a source node S. Asterisk. Create a sink node T. 2. Edges from source asterisk. Asterisk. For each node, cell, in set A, add an edge from the source S to that node with capacity 1. 3. Edges to sink asterisk. Asterisk. For each node, cell, in set B, add an edge from that node to the sink T with capacity 1. 4. Edges between A and B asterisk. Asterisk. The edges we created based on adjacency between cells in A and B remain, and each has a capacity of 1. 5. Run max flow asterisk. Run a max flow algorithm, example Edmonds-Karp, Dynex, or Ford-Fulkerson with appropriate improvements, from the source S to the sink T. 6. The result asterisk. The maximum flow value is equal to the size of the maximum matching, which is the maximum number of dominoes you can place. Why does this work? Asterisk. Each edge from the source represents a potential domino starting at a cell in set A. The capacity of 1 ensures that a cell in A can be part of only one domino. Asterisk. Each edge to the sink represents a potential domino ending at a cell in set B. The capacity of 1 ensures that a cell in B can be part of only one domino. Asterisk the edges between A and B represent the valid domino placements. C++ code example, Edmonds carp using adjacency matrix. Explanation of the code asterisk. 1 includes necessary header files for input/output, vectors, and queues. 2 constants *max_n defines the maximum possible number of nodes in the graph. 3 variables *n, m, dimensions of the grid. *grid, 2D array to store the grid, or x. *capacity, adjacency matrix representing the capacity of each edge in the flow network. Initialized to 0. *parent, array to store the parent of each node during BFS, used for path reconstruction. 4 get node index, int row, int col, * converts the row and column of a cell into a unique node index for the graph. We add 1 because the source node is at index 0. 5 BFS, int s, int t, int number nodes, * performs a breadth first search, BFS, to find an augmenting path from the source S to the sink T. An augmenting path is a path with residual capacity. Returns true if a path is found, false otherwise. 6 max flow, int s, int t, int number nodes, * implements the Edmonds carp algorithm to calculate the maximum flow from the source S to the sink T. * it repeatedly calls BFS to find augmenting paths. * for each augmenting path, it finds the bottleneck capacity, minimum capacity along the path. * it updates the residual capacities of the edges in the path. * returns the total maximum flow. 7 main, *. * reads the input grid dimensions, n, m, and the grid itself. * calculates the total number of nodes in the flow network. * initializes the capacity matrix to 0. * builds the graph. * iterates through each cell in the grid. * if the cell is empty, dot. * calculates its node index, u. * adds an edge from the source to node u, if I plus j is even. * adds an edge from node u to the sink, if I plus j is odd. * checks the 4 adjacent cells, up, down, left, right. * if an adjacent cell is empty and is in the other part of the bipartite set, adds an edge between the corresponding nodes in the graph, with capacity 1. * calls max flow, to compute the maximum flow. * prints the maximum flow value, which is the maximum number of dominoes. How to compile and run *. 1. Save * save the code as a .cpp file, example cram.cpp. 2. Compile * use a C++ compiler, like G++, to compile the code. 3. Run * execute the compiled program. 4. Input * when prompted, enter the input from the problem statement. Important considerations and optimizations * memory usage * for larger grids, up to 100x100, an adjacency matrix might consume a significant amount of memory, and (2). For very large grids, consider using an adjacency list representation instead, which can be more memory efficient, especially if the graph is sparse, i.e., not every node is connected to every other node. Algorithm choice Edmonds carp is a relatively simple algorithm, but its time complexity is V e2, where V is the number of vertices and E is the number of edges. For larger grids, algorithms like Dynix algorithm or the Hopcroft-Karp algorithm, specifically for bipartite matching, may provide better performance. Dynix algorithm is often a good choice and can be implemented with a time complexity of V(2)(e), which simplifies to and (3), in our case, since E is O, N, and V is O, N. Asterisk correctness asterisk double check your edge construction to make sure you are correctly creating the bipartite graph and adding the source/sink edges. Asterisk clarity asterisk use descriptive variable names and comments to make your code easier to understand. Asterisk testing asterisk test your code with various input cases, including small grids, larger grids, grids with many block cells, and grids with few block cells. Asterisk coordinate system asterisk be very careful about off-by-one errors when converting between grid coordinates, row, COL, and node indices. Asterisk bipartite condition asterisk verify that your implementation enforces the bipartite property, where edges only connect cells with different parities of row plus COL. Alternative code example, Dynex algorithm using adjacency list. Here's a sketch of how you might implement the same solution using Dynex algorithm with an adjacency list representation for potentially better performance. Dynex algorithm enhancements asterisk. Asterisk adjacency list asterisk uses vector int adjective to represent the graph's adjacency list. Each element adjective U is a vector of indices into the edges vector, indicating the edges originating from node U. Asterisk edge structure asterisk the edge struct stores information about each edge, destination node, capacity, flow. Asterisk add edge, a helper function to add edges, including back edges, to the graph. Asterisk BFS, level graph BFS is used to construct a level graph. The level array stores the shortest distance, number of edges, from the source to each node in the residual graph. Only edges that lead to nodes at the next level are considered in the DFS. Asterisk DFS, blocking flow DFS is used to find blocking flows. A blocking flow is a flow that saturates at least one edge along every path from the source to the sink in the level graph. Asterisk PTR asterisk the PTR array is an optimization that avoids re-examining edges that have already been saturated in the DFS. PTRU keeps track of the next edge to examine in the adjacency list of node U. Dynex algorithm is a more efficient max flow algorithm compared to Edmonds-Karp, especially for larger graphs. In summary, the cram problem is a great example of how a seemingly geometric problem can be elegantly solved using graph theory and network flow techniques. By understanding the connection between domino placements and maximum matchings, you can apply standard max flow algorithms to efficiently find the solution. Remember to consider the memory usage and performance characteristics of different algorithms and data structures when choosing your implementation. Good luck.